Chapter 16c, Acid-Base Properties of Ions and Salts, Polyprotic Acids, and Acid Strength and Molecular Structure. Now we noted in the chapter on acid-base that the stronger the acid, the weaker its conjugate base, and vice versa. So above the hydronium-water equilibrium, we have the 6 strong mineral acids, in which the hydrogen is only weakly bound to its anion and is easily removed to form a bond with the unshared pair of electrons on the water molecule to form the hydronium ion. So this hydrogen anion bond here with these 6 strong mineral acids is very weak. Therefore, the anions necessarily are extremely weak bases. The very thing that made them able to give up a proton make them reluctant to take one back on. As we go further down the list, the bond between hydrogen and the anion strengthens, and the acid consequently becomes weaker. We can show this effect using a color-coded strip like this. And of course, as the bond between hydrogen and the anion becomes stronger, the conjugate base of that acid becomes stronger as well and more willing to take on a proton. So as we go down this list, the acids become weaker, but the base strength becomes stronger because the anions are better able to form a bond with hydrogen. Therefore, salts, or anions, of weak acids react with water to form some hydroxide ions. The weaker the acid, the more hydroxide will be produced from its conjugate base and water. We're going to look at the relationship between the Ka of an acid and the Kb of its conjugate base. Here's the familiar ionization of an acid in water, forming its conjugate base and the hydronium ion. And here is its mass action equation. Below it, we have its conjugate base reacting with water, forming the weak acid and the hydroxide ion. And the mass action equation for that is given here. Now, what would happen if we added these two reactions? We see that the acids would cancel each other out as we added them, and the bases would cancel each other out. And lo and behold, what we're left with is the water equilibrium. How would that play out with the mass action equations? When you add equations, you multiply the equilibrium constants, represented by the mass action equations. So if I take each one of these mass action equations and multiply them together, what happens? The anions cancel out and the acids cancel out. And lo and behold, we're left with the mass action equation for the water equilibrium, which is Kw. So that's how the equilibrium constant for an acid times the equilibrium constant for a base is equal to the equilibrium constant for the autoionization of water, Kw. 1 times 10 to the minus 14. Okay, so the Ka for acetic acid is 1.8 times 10 to the minus 5. So calculate the Kb for its conjugate base, the acetate ion. Turn your playback off, do the calculation, and choose one of these answers. Then come back and we'll discuss it. So here is the answer. Here's the relationship between Ka and Kb for a conjugate acid-base pair. So you would plug in the equilibrium constant for Ka and solve for Kb. Answer is going to be 5.56 times 10 to the minus 10. So let's look at acid-base properties of ions and salts. First off, +1 and +2 cations that are the counter ions of strong bases are pH neutral. So for example, the sodium and sodium hydroxide has no effect on the pH. Or the potassium and potassium hydroxide. Those are +1 cations. Or the calcium ion and calcium hydroxide is pH neutral, no effect on pH. Anions that are the counter ions of strong acids are also pH neutral. For example, the chloride, which is the counter ion in hydrogen chloride, is pH neutral. Nitrate, again, is a counter ion of a strong acid, and nitrate is pH neutral. Or perchlorate, ClO4- is pH neutral. We've seen that anions can be weak bases, but cations can be weak acids. For example, the conjugate acids of weak bases, when dissolved in water, can form a slightly acidic solution. The ammonium ion, for example, which is the conjugate acid of ammonia, right? Ammonia has a pair of electrons, takes on a proton from water, and becomes the ammonium ion. But if you put an ammonium salt in water, it will dissolve to form a little bit of hydronium ion and make the solution a little bit acidic. Same thing with ammonia analogs in organic compounds, like the salt of ethylamine. Dissolve it in water and it will form a slightly acidic solution. Here's the conjugate acid of a weak base reacting with water, forms a little bit of hydronium ion plus the conjugate base. Also, small highly charged cations, like the aluminum ion or the ferric ion, can react with water to form a somewhat acidic solution. These ions are such powerful electron pullers that they pull electrons away from the oxygen-hydrogen bond in the water molecules that are surrounding the ion. And one of these protons may be captured by a water molecule to form the hydronium ion, making the solution somewhat acidic. So this occurs with small, highly charged cations like aluminum ion or ferric ion. Okay, we're going to classify each as acidic, basic, or neutral. The first one is the conjugate acid of an organic amine. It will dissolve in water to form a small amount of hydronium ion, so it will be an acidic solution. Calcium ion will be neutral. The chromium ion is a highly charged small metallic ion, and it will produce a slightly acidic solution. The fluoride ion will dissolve in water to form a small amount of hydrogen fluoride and the hydroxide ion. It is a weak base. Again, classify each as acidic, basic, or neutral. Sodium chloride, neither the sodium ion nor the chloride ion is going to react with water one way or the other. It will form a neutral solution. Calcium carbonate, the calcium has no effect, but the carbonate is a weak base and will form a basic solution. Aluminum nitrate, the aluminum ion is a small, highly charged metallic ion which will react to form a slightly acidic solution. Ammonium chloride, the ammonium ion is the conjugate acid of ammonia. It will react in water to form a small amount of hydronium ion. So the solution will be slightly acidic. Now what about determining the pH of polyprotic acid solutions? Acids that have more than one acidic hydrogen. For most polyprotic acids, the first ionization constant is much larger than the second, which in turn is larger than the third if a third acidic hydrogen is present. That's because the bonds to any remaining hydrogens are stronger as the negative charge on the anion increases. So the first ionization, at least for our purposes, controls the pH. In this class, we shall ignore the second and third, if any, ionizations. So calculate the pH of a 0.1 molar solution of the diprotic acid ascorbic acid, which you may know as vitamin C, where the first ionization constant is 8 times 10 to the minus 5, and the second is 1.6 times 10 to the minus 12. Turn your playback off, try it, come back, and then we'll discuss it. Okay, so here is how you would set up the problem. You'd set up your ICE table. Initially 0.1 molar of the ascorbic acid, change minus X molar of the ascorbic acid reacts to form X of hydronium ion and X of the anion, and at equilibrium 0.1 minus X remains of the ascorbic acid, and X of hydronium and X of conjugate base. Plugging those values into the mass action equation, and then using our X's small approximation, because the K value is so small, we solve for X and end up with 2.8 times 10 to the minus 3 as our hydronium ion concentration. Checking the validity, we divide the amount that is ionized by the initial concentration, and we get a percent ionization of 2.8%, which is less than 5%, so it is a valid approximation. Therefore, the hydronium ion equals 2.8 times 10 to the minus 3 molar, and the pH is 2.55. Trends in the strengths of binary acids. Well, binary acids are made up of two elements and polarized this way, in which the hydrogen is slightly positive and the anion is slightly negative. The more polarized the bond, usually the more acidic the bond is. Hydrogen fluoride is an anomaly because of the small size of the fluorine atom. Hydrogen and fluorine are able to overlap their orbitals very well and form an unusually strong bond. The stronger the bond between hydrogen and the anion, the weaker the acid is going to be. Binary acid strength increases to the right across a period. So as you go from HC to HN to HO to HF, the acid strength increases because the electronegativity increases as you go from left to right. Binary acid strength increases also as you go down a column. That's because as the anion becomes larger and larger, the overlap with the hydrogen orbitals becomes weaker and weaker, and therefore the acid becomes stronger. Now we're going to discuss the strengths of oxyacids with a general formula like this. You have an acidic proton attached to an oxygen, which in turn is attached to a central element surrounded by either no other oxygens or one other oxygen or two or three other oxygens. The more electronegative the Y central atom, the stronger the acid is going to be, because the electronegative central atom will pull electrons away from this hydrogen-oxygen bond, weakening the bond and promoting the ionization of the acid. The second trend is that the more oxygens attached to the central element Y, the stronger the acid is going to be, because the highly electronegative oxygen atoms further weakens and polarizes this hydrogen-oxygen bond. So what I want you to do is consider all of these oxyacids and list them in order of increasing acidity. Turn the playback off, try it, and come back and we'll discuss it. All right, so here we go. First of all, the three compounds which only have the oxygen-hydrogen bond are listed in order of increasing electronegativity of the halogen atom. So HOI is the weakest, HOBr is next, and HOCl is next in terms of acid strength. Now we begin to add surrounding oxygen atoms to the central chlorine atom, and the more oxygen atoms we add, the more these electronegative oxygen atoms weaken the hydrogen-oxygen bond, and so the acid strength increases as we add more oxygen atoms. We've looked at acid-base theory from the perspective of Bronsted-Lowry and from Arrhenius. The Lewis acid-base theory focuses on electron sharing rather than the sharing of a proton. It defines the electron donor as the Lewis base, which is a nucleophile, literally a species that loves a nucleus, and after all, a nucleus is where the proton is. So a Lewis base is a species that has a lone pair of electrons that can be donated. The Lewis acid is an electron acceptor, and it's an electrophile, literally loving electrons. It itself is electron deficient. It has an orbital which can share with a pair of electrons. So what happens is a Lewis base donates a pair of electrons to a Lewis acid, and a covalent bond forms between the particles. The product is called an adduct. So here's a question. Identify the Lewis acid and Lewis base when a water molecule reacts with ammonia molecule. What happens, of course, is that the water molecule donates a proton to the lone pair of electrons on ammonia. It forms the ammonium cation NH4+, and the hydroxide anion OH-. So which is it? Is water the Lewis acid and ammonia the Lewis base? Or is Lewis acid ammonia and water is the Lewis base? Which one? The electron donor in this story is ammonia with a pair of electrons that are being donated. The electron receiver is a proton from the water molecule. The proton has an empty orbital which can accept a pair of electrons from ammonia. So water is the Lewis acid and ammonia is the Lewis base. Here's another one. Which line identifies the Lewis acid and the Lewis base? You have ammonia reacting with aluminum trichloride, forming this adduct. So is the Lewis acid ammonia and Lewis base aluminum chloride, or vice versa? Okay, ammonia still has a pair of electrons it is donating. That makes it a Lewis base. Aluminum has a space available for sharing a pair of electrons. That makes it a Lewis acid. So the Lewis acid is aluminum trichloride. The Lewis base is ammonia.